Assalamu alaikum, guys. Good morning. Welcome back to Inspired Teens Physics for grade 12. In today's lesson, we'll be covering the Doppler effect. Okay. Okay, before we start, can you guys please confirm if you guys can hear me and that you guys can see my screen and that everything is clear, please? Okay, cool. Perfect. Thank you so much. Okay, cool. Let us begin. Okay, so Doppler effect, right? This is a relatively easy section. It doesn't really entail much. Has a little bit of theory, some calculations, and the hardest question is simple as well. Okay, so let's start off. Let's go through it. Let's start off by reading the definition of Doppler effect. Doppler effect is defined as an apparent change in the frequency detected by a listener due to relative motion between the sound source and the listener. Okay, so basically what happens here in Doppler effect, okay, is when the word relative motion, okay, we'll define relative motion. That's important for us to understand what that means. Okay, so yes, an apparent change in the frequency detected by the listener. Here we have two things. We have a sound source, okay, and we have a listener. We have a sound source and we have a listener. So the sound source could be, for example, an ambulance, okay, or a siren, or anything that emits a sound. And the listener is the person or the detector that is taking in the sound, okay, listening to the sound. Okay, so we have two different entities. One is a sound source, one is a listener. And apparent change in frequency detected by the listener. So we're talking about what frequency is detected by the listener, okay, when there is relative motion between the sound source and listener. So the important thing here is that relative motion means that they are traveling at different velocities. Yes, YS, I don't know. Okay, but relative motion, yes, basically means that they're traveling at different velocities. So for example, we could have a sound source which is stationary and a listener that's driving towards it. Okay, so maybe the listener is someone in a car or walking towards the sound source. We could have the listener walking away from the sound source. Alternatively, we could have a stationary listener and a sound source that is moving. We could even have both moving, but Doppler effect will only be observed when they are at different velocities. Okay, so if the sound source and the listener are both traveling at a certain speed, provided that they are traveling with different velocities, Doppler effect will be observed. Okay, so hopefully we can understand this more as we go along. But one more time, an apparent change in the frequency detected by a listener due to relative motion between the sound source and the listener. So one more thing to note is, yes, this apparent change in frequency. So when there is relative motion, so let's just say we have a sound source. I'll just write here, I'll erase it. Just say we have a sound source, right, an ambulance. Okay, we have an ambulance, okay, and we have a stationary listener. So if they are both stationary, okay, what happens is the frequency that this siren emits, let's just say it's 200 hertz, okay, and the listener, let's say he's listening. Okay, that does not look like an ear. Okay, we don't have to. Let's give this listener a detector. Okay, this is a sound detector. Okay, when they are both stationary, so if you have a stationary listener and a stationary sound source, this is this beautiful ambulance in this case. Okay, when they are both stationary, the sound source emits 200 hertz. Okay, and the detector would detect 200 hertz as well, which makes sense. Okay, the sound source that's being emitted is 200 hertz, right? But and the detector is detecting 200 hertz as well, right? Like to say they're not that far apart, and the ambulance is emitting 200 hertz of sound, and the listener is detecting with the detector 200 hertz of sound. Okay, this is when they are both stationary. So in this case, there is no relative motion between these two objects. Okay, so this has no Doppler effect. All right, here there's no Doppler effect observed. Why? Because they are both traveling, they are both stationary. There's no relative motion between the two, meaning they're not traveling at different velocities. Okay, so when both are stationary next to each other, okay, whatever the sound source emits, whatever frequency of sound it emits, that's what the listener or a detector would detect, the exact frequency. But now this changes when there is relative motion. So let's just say let's just copy this. Let's just say we keep the listener stationary. Okay, if we keep the listener stationary, but now this ambulance, okay, it starts traveling towards the listener. So this velocity changes. This ambulance, before it got there, let's just say, it started traveling towards the listener, okay, with a constant velocity of 5 meters per second. Okay, so it starts traveling towards the listener. Okay, remember, it's still emitting 200 hertz, right? That hasn't changed, because the only way to change how much the sound source emits is to actually change the sound source, right? Because it's a siren, it's a constant siren. They didn't change the siren. That siren, the sound source will always emit that same amount of hertz. So in this case, that particular siren is always going to emit 200 hertz of sound. But now, yes, the key here is that this guy is moving towards the listener. Okay, and in this case, all right, so this guy emits that. In this case, right, because it's moving towards the listener is still stationary. Now we can clearly see that the listener and the sound source are traveling at different velocities, meaning there is a relative motion between listener and sound source. Now, this is when things change, right? Instead of detecting the exact amount of hertz, it would actually detect more. So let's just give an example, and let's just say it detects 210 hertz of frequency. So this is what happens. This is what we can observe when there is relative motion between a sound source and a listener. Okay, so let's just go back to the first one. In the first one, both are stationary. So we said that when they are both stationary, meaning there is no relative motion, and we'll do another example of this. Okay, there's no relative motion between the listener and the sound source. Okay, and because there's no relative motion, again, which means they're not traveling at different velocities, and in this case their velocity is both zero. Okay, so that's the key thing here. Then whatever the sound source emits, whatever frequency it emits, that's the same frequency that we can detect as a listener, and in that case there's no Doppler effect that's observed. Okay, however, when there is a relative motion in the second case, right, now the sound source hasn't changed. It's still the same ambulance emitting 200 hertz, but now it is moving towards the listener at 5 meters per second. Okay, again, it needs to be a constant velocity. For now, we'll say the velocities don't matter. But when it moves towards the listener, that's when Doppler effect occurs. Okay. Doppler effect occurs in this case, and the frequency that is detected by the listener is actually higher than the actual frequency emitted by the sound source. So that's another key thing, which we'll discuss a little more. So in this case, there is relative motion, which means basically that they're traveling at different velocities. There is relative motion between listener and sound source. So because it's moving towards, okay, we'll note this properly later, but I'll just tell it to you for now. When it moves towards, the listener detects a higher frequency. And let's just look at the definition of the Doppler effect once more. It's an apparent change in frequency detected by the listener due to the relative motion. So apparent also kind of means like fake change, right? It's not an actual change in the frequency of the sound source. It's just apparent because of the relative motion. The frequency detected by the listener is changed compared to the original frequency emitted. Okay, and coming back here, yes, it is actually higher when the sound source is moving towards the listener. Let's look at the same example. But in this case, let's just say that the ambulance, will I be able to? I don't think I'll be able to flip it. Let's just do this. Okay, let's just say now the ambulance is moving in which direction? The ambulance is moving away from the listener. Okay, so this holds true still. There is relative motion, okay, between these two objects. Okay, because one is traveling at a velocity of maybe, let's just say this time -5, right? Or we can consider speed, right? We'll be able to tell. Okay, now the ambulance or the sound source is moving away from the listener. This means that there is still a relative motion because the listener is still stationary. It still has a velocity of 0. But now in this case, the ambulance has a constant speed of, let's just say 5, constant velocity of -5. They'll generally give it in terms of speed. The key thing is the direction in which it's traveling. Is it traveling towards or away? That's the big thing in this section you have to understand. Okay, and in this case, it's traveling away. So let's write here, this is towards, right? And then this is away. Okay, so while it's traveling away from the listener, because there is relative motion, according to Doppler effect, there will be an apparent change in the frequency detected by the listener. And this apparent change this time is actually lower. Let's just say 185 hertz. It's lower than the actual frequency emitted by the sound source. Okay, because it's moving away from the listener. Yes, there's relative motion. Yes, Doppler effect will occur. Okay, Doppler effect will occur. Okay, and the frequency detected by the listener is going to have a change to it, and because it's moving away, it's going to be lower than the actual frequency. Okay, so this is just a quick rough diagram to explain basically what goes on with Doppler effect and what do we mean by an apparent change, okay, by the apparent change in the frequency detected by the listener due to relative motion between the sound source and the listener, right? So that definition of Doppler effect really makes sense once you look at it in terms of this diagrams, right? We can see that there is a change detected by the listener as soon as there's relative motion between the two. Okay, and we said when it's moving towards, then we call this, we'll discuss these terms in a bit. Let's just call this guy FL, right? FS, frequency of the source. Okay, and let's just call this guy frequency detected by the listener. So, okay, in this case here, the frequency detected by the listener is actually greater than the actual frequency of the source. Okay, that's what happens when it moves towards. And in this case, the frequency detected by the listener is actually less than the frequency of the source. Okay, please note that in the second two cases, because the frequency of the listener is more in the second case and less in the third case, it does not mean that the actual frequency is changing. Okay, what stays the same is this frequency this frequency emitted by the source. Okay, it stays the same. The source still emits 200. It still emits 200 here. The reason we are detecting differently, okay, is because of this relative motion between the two. Okay, that's the key thing. So if you want to change the frequency that the source emits, you have to change what the source is. Maybe you change it from an ambulance siren to a bus hooter, for example. Then, of course, those two would probably emit different frequencies, right? Or you choose a different sound source, so you somehow change that frequency. But because the listener is detecting different frequency, that's just the only reason it's detecting different frequencies is because of the relative motion between the two. Okay, it's not specifically because the sound source frequency has changed. Okay, so that's just a quick little diagram to describe the Doppler effect. Now, in Doppler effect, we deal with a formula. Okay, and we have FL, which tells us the frequency of the listener. Okay, so this here is frequency detected by the listener. Frequency detected by the listener. Okay. Then we have Fs, which is actual frequency, which we sometimes refer to as actual frequency, emitted. Okay, so not detected. Emitted means released, sort of. Actual frequency emitted by the sound source. Okay, that's why it's Fs, frequency of the source. Okay, then we have three different velocities. So this is the velocity of the, you can guess, the listener. Okay, so what velocity is the listener traveling at? Is it the stationary listener? Is the listener someone in a car that's traveling at a certain velocity? Okay, and then source is velocity of source of the sound source. Okay, we could also have perhaps a stationary sound source. Okay, and then this V is the speed of sound. It occurs twice. Okay, the speed of sound in air. Okay, it normally has a constant which we use as 343 or 340, somewhere around there. They'll tell you what to use it as, or sometimes you can even, they'll make you calculate it and you should expect the answer around 340. Okay, but yes, this is basically the formula we use, right? It's not so complicated. The formula is given. Okay, and yeah, these are all the annotations of what each variable means. Okay, so before we go on and discuss the different cases, let's just discuss something about like some revision about period, wavelength, and frequency, right? These are all important terms that we need to understand because they expect you to remember this from previous grades, and they might give a question which requires a little bit of this knowledge to do a little bit of calculations to then get into this formula, for example. Okay, so let's just discuss the three and look at their definitions. Period, wavelength, and frequency. The first thing we're going to discuss is period. It's represented by a symbol T. Okay, period is in seconds, and the definition for period is the time taken for one complete wave. The time taken for one complete wave. Okay, let's talk about wavelength. Wavelength is the length of one wave. Okay, and frequency is the amount of waves in 1 second. Wavelength is in meters, frequency is in hertz. Okay, so all important definitions which you have to know in this section. Okay, so yes, let's look at the difference quickly between frequency and period. So period is the time taken for one complete wave. So one complete wave looks like this. Okay, however, frequency is the amount of waves in 1 second. So in 1 second, how many waves? So you could have 50 waves in 1 second. You could have 2 waves, 1 wave in 1 second. Okay, but when it comes to period, that's just telling us the total time for one complete wave. Okay, and then let's have a look at this formula. This is a general waves formula. Okay, and in this section, because you'll see that we'll do this in photoelectric effect as well. In this section, C is equal to F times lambda. We're going to use C is a speed. Okay, so sometimes it's the speed of a wave. Now, remember, you get light waves and you get sound waves. Right? Is there any other waves we deal with specifically in metric? I don't think so. Yeah, I don't think so. Right, but for now, this is the wave formula that you're going to either use for sound or light, because both are waves. In this section, you will use this as the speed of sound in air specifically. Okay, and it is given as, or it's approximately around 343 meters per second, sort of like a constant, right? Sometimes they tell you use it as 340, sometimes maybe 335, sometimes 300, right? Just look out for that. They'll tell you what to use it as in the question. Sometimes they'll ask you to calculate it. Okay, and of course this guy is frequency, and this guy is wavelength, right? Okay, so the speed can be calculated by multiplying the frequency and the wavelength. Okay, and this is just extra information to note. Sound is a longitudinal wave, which basically indicates as well that it needs a medium to travel. Okay, so sound needs a medium to travel. Okay, so if you think about space, if you think about the vacuum in space, right? In a vacuum, there's no particles like in space, for example, right? There's no particles. So that's why sound does not travel through space. Okay. That's why astronauts, just for interest's sake, use intercoms and they don't shout at each other through space, even if they're next to each other. Okay, it's because sound is a longitudinal wave and it requires a medium. So on Earth, the medium is the air. Okay, the air particles, sound bounces off each air particles and travels that way. Okay, so yes, it's a longitudinal wave which requires a medium. Okay, so this formula helps us to create the indirect proportion or inverse relationship between frequency and wavelength. Okay, because C is constant. It doesn't stand for constant. C is a speed, but it's a constant, right? Speed of sound in air, we use a constant value. So therefore, if this has to stay the same, if you're going to increase this, you're going to have to decrease this, and vice versa. If you're going to decrease this, you're going to have to increase this. So this tells us that they have an inverse relationship. So that's important to know. The bigger the frequency, the smaller the wavelength. The bigger the wavelength, the smaller the frequency. Now, I want you to understand this concept. So we're going to discuss it in terms of what? We're going to discuss it in terms of this diagram. So I'm going to put a 1 second marker here. Okay. And the first thing we're actually going to discuss is period versus frequency. So if I have, okay, we can discuss that at the end. Okay, let us discuss the first thing. Okay, let's get rid of this and make one wave. One second. Okay, so let's just say we have one complete wave in 1 second. Now, when we talk about frequency's definition, it says the amount of waves in 1 second. So how many waves do we have here in 1 second? We have one wave. So the frequency of this guy, okay, is 1 hertz. Literally, its frequency is 1 because it's one wave in 1 second. So its frequency is 1. Okay, then we can talk about the next type of wave, right? Let's do double the amount of waves. Shucks. Okay, my waves are not perfect, but in this case, now we can see that we have completed 2 waves in 1 second. So this is 2 hertz. Okay, then let's talk about period. The time taken for one complete wave. So for the red wave, the time it takes for one wave to complete is 1 second. So period is 1 and frequency is 1. Okay, in the red case. What about the green case? Okay, in the green wave, there's 2 waves that's completed in 1 second. That means one wave takes 0.5 seconds. So therefore, the period is 0.5. Okay, there is a relationship between period and wave, and it is what in the world? Okay, you can calculate. So period is equal to 1 over frequency, and frequency is equal to 1 over period. As simple as that. Okay, so you can calculate one of the two if it's given. Okay, so please be able to read this graph, right? And the easiest way to be able to read this graph is understanding the definition of period, understanding the definition of frequency, as well as wavelength. Okay, so period is how many waves in 1 second, while, sorry, frequency is how many waves in one second, while period is the time it takes for one complete wave, or the time it takes for one wave to complete. Okay, so just keep that in mind. Okay, and the other thing is I want to show you the relationship between frequency and wavelength. Okay, so here I have 1 hertz of frequency. Okay, I have 1 hertz of frequency, so the wavelength is a decent size, right? If we have to continue it, each wave would look the same, right? 1 complete wavelength is from here, the start of the wave, to the end of the wave. Okay, but what happens when I do that? What happens when I when I up the frequency? So now instead of having 1 wave in 1 second, I have 2 waves in 1 second. What happened to the wavelength? In order to fit more waves in 1 second, we have to sort of compress that wavelength. We have to squash it down. And now, as you can see, the wavelength of a single wave is half. The wavelength of a single wave is less compared to the original case. Okay, of just having that. Okay, here we have 1 hertz of frequency, so we fitted 1 wave in 1 second, and when we fit 2 waves in 1 second, we have to sort of compress it to half its size. So clearly you can see that the wavelength decreases. So as we fit more and more waves in 1 second, our wavelength has to decrease. So the higher the frequency, the lower the wavelength. I hope that is clear now. Let's just do a quick example. It's a siren. A siren emits a sound of a wavelength 0.4 meters. What is the frequency of the wave? So this is where we use our little wave formula. Okay, and we say C is equal to F times lambda. C is 343. F is what we want to calculate, and lambda is 0.4. So when we do this calculation, we get the frequency of the siren, or the source of sound, as 857.5 hertz. Okay, so that was just a quick example, right? Because oftentimes you see in this section, what do we work with? We work with only frequencies, but sometimes they give it to you in terms of wavelength, so you can use this simple formula to convert from wavelength to frequency. Okay, so that's why we started off with this basics. Right, revision of the basics done. Let's move over to grade 12 work. Right, let's discuss some things we already discussed, but we're going to put it nicely formally. So, and just to revise it once more. So when the source is moving towards the listener, or vice versa, meaning the listener is moving towards the source, okay, when there's this towards motion, then the frequency detected by the listener is greater than the frequency of the source. Okay, keep that in mind. Remember, we looked at the example over here. When it's moving towards, it detects a higher frequency. When it moves away, it detects a lower frequency, and that's what's discussed here. When the listener is moving away from the source, that's here. When the listener is moving away from the source, then the frequency detected by the listener is actually less than that the actual source emits. Now, if you look at this formula, you'll notice we have a plus minus, meaning that we have options, okay? And here's how we work with those options. So when the listener is moving towards the source, okay, we put plus at the top, minus at the bottom. When the listener is moving away from the source, we put minus on top, plus at the bottom. As simple as that. Okay, please remember these are all vice versa, meaning if the source is moving towards the listener, okay, you just need to be able to detect some sort of what? Some sort of towards motion. That's all. Okay. But yeah. Okay. So these are important. You need to write this out, okay, to get a mark for writing the correct formula, either plus or minus. Okay, so please, you need to know this. The formula is given, but when it's towards, you need to put the plus on top and the minus at the bottom. When it's away, you need to have a minus on top and the plus at the bottom. Let's look at this in terms of sound waves. Okay, so in this first case, again, we have a towards motion. So you can see this little cut, which is the sound source. Okay. Which is the sound source. Okay. And it's okay, sound. And it is moving towards. Okay, the sound source, oops. The sound, yeah. the sound source is moving towards the listener. Let's just say this is Dylan from the chat, by the way. Hopefully he's awake. Okay. The sound source is moving towards this person. This diagram is describing what happens to the sound waves. Okay. So firstly, as you know, the frequency of the listener is greater than the frequency of the source. So that's exactly what we are noticing in this diagram. Okay. You can see that the sound sources more towards the listener become compressed, right? Mean they're closer together. So what that means is that this is the end of the higher frequency end. Okay, so more towards the listener, because the frequency detected by the listener is greater when it's moving towards, right? Then you will observe this type of diagram that the sound waves become more compressed towards the listener because its frequency is higher than that of the source. So the wavelengths here, or the frequency is much less because you are seeing a less condensed space of waves, right? Remember, we're trying to fit more waves in a tighter space. That represents higher frequency, and that's what can be observed here. That when the sound source is moving towards, the frequency of the sound sources, the frequency of the sound waves, become more compressed towards the listener. Why? Because the frequency that the listener detects is larger than that of the source. Right? I hope that this is making sense. Okay, what about in this case? Right? Now it's on opposite ends. Okay, what happens is the sound source, the ambulance, or whatever this is now moving away. So let's just say this is still the sound source. Okay, and this guy is moving away from the listener. Let's just say this is Akifa. Okay, and this ambulance is moving away from the listener. Okay, now what you observe with the sound source is that by the listener, okay, the sound waves are less compact, okay, less compressed, which means there's a lower frequency on the listener's end. Okay, this is the listener. Okay, and and so too is this the listener. Okay, and yes, this diagram shows how the sound waves behave when a sound source is moving away. The waves become more compressed towards the sound source. So you can notice a pattern. The sound waves become more compressed towards the one with the higher frequency, and we know that when it's moving away, the frequency of the listener, I'm going to lose my mind. The frequency of the listener, right, is less than that of the source. So meaning the source has a higher frequency than the listener. Remember, it is only an apparent change that the listener detects. Okay, it's not an actual change to the frequency. It's just that you detect a lower frequency. Okay, so I hope that makes sense. So that's how the sound waves behave when listener sound source moving towards and moving away. Okay, what about no relative motion? Now, this is important. Your actual frequency is detected. This is very important for us to understand. When there is no relative motion, then we discussed this. This is the first thing we discussed. Okay, there is no relative motion between the sound source, the listener, right? Let's just say here we have Nusaiba. Okay, the listener. Okay, and let's just say here we have an ambulance. So I don't know, maybe Nusaiba has a Ferrari, and the Ferrari is hooting for some reason. But here they both have no velocity. Or alternatively, one thing we didn't discuss, okay, is if they are traveling at the same velocity. Okay, we'll discuss that in a bit. But yes, here there is no relative motion between the listener and the sound source. Okay, let's just clarify that this is indeed the sound source. Okay, and this Ferrari is hooting for some reason. Maybe Nusayba is standing in the middle of the road and this guy is hooting to get out of the way. Okay, but they both stationary. Okay, and actual frequency is detected, meaning the frequency that the listener observes will be equal to the actual frequency emitted by the sound source. Okay, and as you can see, what is the behavior of the sound waves? They are equally dispersed, right? They're not like more compressed on one end and less compressed on the other end. They are like equally dispersed. I know this diagram is not perfect, like perfectly dispersed, but you should understand that there's no change in the sound waves. They are equally dispersed, as you can see in this case, right? So you will be asked to draw these diagrams at times. So that's why you need to understand how they work. So by the way, no relative motion, as we discussed previously, could mean that they are both stationary, or alternatively, they are both traveling at the same velocity. So let's just say we have Nusayba traveling in her Ferrari on the highway. Okay. Let's make it cool, I guess. That's definitely how Ferrari looks. Let's just say we have this ambulance who's rushing for an emergency, but obviously Nusayba being in a Ferrari can travel just as fast as the ambulance. Okay, but now let's just say they're both traveling in the same direction. Okay, because remember velocities. If they were traveling in opposite directions, that wouldn't be the same, right? Because they're still moving away from each other. And let's just say that they're both traveling at the same speed. Right? One is traveling for an emergency, one is just driving fast because they have a Ferrari. But nevertheless, right, if they're traveling in the same direction, right, on this road, and they're both traveling at the same speed, then we need to understand that here there is also no relative motion. So here Doppler effect will not occur. Okay, and the frequency detected by the listener will be equal to the actual frequency emitted by the source. So the key thing to note here is no Doppler effect. So there won't be an apparent change in the frequency detected by the listener due to there being no relative motion between the two. Okay, please, I hope that this is making sense so far. Please stop me if you don't understand anything. Okay, let's just quickly discuss this theory, and then I want to go into a question. Okay, so there is some theoretical aspect. Okay, wait, maybe we can always come back to this. Yeah, we can come back to this if we have another lesson on it. It's fine. Okay, let's just discuss it, and we should be able to do a question as well. Okay, so now we're going to discuss some more theoretical aspects of it, right? Where we've previously discussed like some practicals. Okay, now you will be dealing with spectral lines. Okay, so if the spectral lines are shifted towards the blue end, okay, this means that the object, okay, we always deal with a distant star. Where is it? Red shifts and blue shifts. Okay, let's define this first and then we can go backwards. So let's define a redshift. What is a redshift? A redshift occurs when the spectrum of a distant star is moving away from the Earth and is shifted towards the red end of the spectrum. Let's discuss blue shift. Occurs when the spectrum of a distant star is moving towards the Earth and is shifted towards the blue end of the spectrum. So besides which end of the spectrum it's shifting towards, here we deal with Earth and we're dealing with a star. Okay, so instead of dealing with two cars or an ambulance and a listener, we're dealing with Earth and a star. So we have different cases for when the star is moving towards the Earth and when the star is moving away from the Earth, right? That makes sense. So red shifts and blue shifts. So this is how like scientists and space specialists, so I forget what they call. Okay, this is how they detect whether a distant star is moving towards or away from the Earth. So let's just go back here. If spectral lines are shifted towards the blue end, so now this is how they detect Again, if a star is moving towards. So if the spectral lines are shifted towards the blue end of the spectrum, that means that it's moving towards Earth. This distant star is moving towards Earth, and we call it blue shifted. However, if the spectral lines are shifted towards the red end of the spectrum, then this means that the distant star is moving away from Earth. We call this red shifted. We'll discuss these definitions again. So let's do blue shifts first. Blue shift occurs when the spectrum of a distant star is moving towards Earth and is shifted towards the blue end of the spectrum. In terms of frequency, the spectral lines are shifted towards higher frequencies, right? We expect that because it's moving towards. When it's moving towards, right, we experience an apparent change in the frequency, which is higher than what it actually is. In terms of lambda, right, remember frequency and lambda are inversely proportional, so the spectral lines would be shifted towards lower wavelengths. Higher frequencies, lower wavelength. That describes that inverse relationship that we discussed. Then we talk about red shifts occurs when the spectrum of a distant star is moving away from the Earth and is shifted towards the red end of the spectrum. In terms of frequency, the spectral lines are shifted towards lower frequencies, moving away. That makes sense. And because it's lower frequencies, in terms of wavelength, it's higher wavelengths. They shifted towards the higher wavelengths. Let's just discuss some uses of Doppler effect. Right, many of them in the medical field. It's used for a blood flow meter, measuring the heartbeat of a fetus. It's a radar gun, which helps to detect speed. In sonar, as well as it's used to determine whether stars are moving towards or away from the Earth. We just discussed this in terms of red and blue shifts. Okay, that concept we'll come back to. Let's do a paper quickly. Okay, question 6. A learner in a car moving at a constant speed of 10 meters per second along a straight horizontal road records the frequency of a sound emitted by a distant stationary source. A lot of information given here. We have the velocity of the listener. So in this case, the learner in the car moving at a constant speed of 10 meters per second along a straight horizontal road records the frequency. This tells us what? This is the listener. They record the frequency. This is the listener. So this is the velocity of the listener. Okay. Then let's read further. Actually, it's in black, so we don't confuse it. Listener. Okay. A sound emitted by a distant stationary source. Stationary source means that the velocity of the source is 0. So this is velocity of the source. Okay, so this is a good way to approach this question or any question. You can highlight key points of information and allocate what variable that indicates to us. In this case, I said that that's the velocity of the listener. This is the velocity of the source. Right, second paragraph. The learner then repeats the recording of the frequency of the sound when the car travels at a new constant speed of 20 meters per second. So, so this car is traveling at a new constant speed of 20 meters per second. Okay, so again, this is still the velocity of the listener because they're changing the speed at which the car is traveling. Okay, the graph below, not drawn to scale, is obtained from the results. This is simultaneous. We don't know the frequency of the source. Can we use any example? Frequency of velocity of listener, velocity of source, frequency of source. Yeah, I think we can use an example. Okay, never mind. So that's fine. The graph below, not drawn to scale, is obtained from the result. So here we have a recorded frequency versus speed of car. Now you must understand, whenever we have like recorded frequency, this is what? This is always the velocity detected by the listener. Okay, so please note, here we have a car. Like a normal looking car for once. Okay, moving towards a stationary sound source. I don't know, let's just throw a speaker, I guess. Okay, stationary sound source and a moving car moving towards the stationary sound source, right? So if you're a visual learner, you prefer drawing a diagram, maybe do that, right? Maybe it will help along a straight horizontal road. Okay, So initially it travels at 10 meters per second, then at 20 meters per second. But if we look at this graph, which shows us the velocity of the listener, because it says recorded frequency, remember velocity of source, that would be actual frequency. Okay, so there's some key things to note, right? What they mentioned in the diagram, it was what they mentioned in the paragraph, when it was traveling at 10 meters per second, it detected, so now from the graph, we can see it detected that frequency, all right, 679.1 hertz. Then we know he sped up. And when they sped up to 20 meters per second, then they detected that frequency there. Okay, so it went from, okay, that's fine for now. We'll discuss that probably next week. Okay, but as you can see, okay, when they're traveling at different speeds, they detect different frequencies. But then we have this frequency here when the graph is extrapolated to here. And this frequency, if we follow it down to try and get its speed at that point, this is when the speed is equal to 0. Okay, so remember this graph is drawn for the car. This is the motion of the car in terms of its speed and detected frequency. Okay, so here the car's velocity is 0. And when the car's velocity is 0, it's detecting 700 hertz. Now, why did I choose to particularly point that out? Because it's extremely important. Okay, so remember, the velocity of the sound source is always 0. We're dealing with a stationary sound source. The quick English thing, by the way, the only English thing that I know. You spell with an A when you're talking about it staying still. You spell with an E when you're talking about the stuff in your pencil case. Okay. Velocity of the source is 0 at that point. Okay, at some point. So before it started moving, okay, initially. So now let's just put it in terms of this diagram. When the velocity of the car is 0, and the velocity of the source is 0, this is a very specific case. This case here. Both are stationary. That means that the frequency of the listener is equal to the frequency of the source. The actual frequency is detected. So you might look through this paragraph and be like, wait a minute, right? We were never given frequency of source, right? Here we have, sorry, this is not velocity of listener. This is frequency of listener. Here we have the frequency of the listener given, but we were never explicitly given the frequency of the source. But this is how you determine it, people, from this diagram, because you can see that at that point, the velocity of the car is 0. And you know that throughout the motion, the velocity of the sound source is 0. So when they both 0, there is no relative motion between the two, right? Remember that the velocity of the listener is also 0. Okay. And in this case, there is what? There is no relative motion. Okay, and therefore the listener frequency detected, the frequency that the listener detects, is equal to the frequency of the source. So we actually have it because at this point the frequency of the listener is 700, so the frequency of the source is 700 hertz. Okay, now when we observe the change, right now it's traveling at 10 meters per second. Remember, when the car is traveling at 10 meters per second, the velocity of the source is still 0. So now there is relative motion because one is traveling at 10 meters per second and one is traveling at 0. Okay, but now how do we determine the direction? Because that's actually the first question. So, okay, so the first question is actually take the Doppler effect. Doppler effect is an apparent change in the frequency detected by the listener due to relative motion between listener and sound source. 6.2, use the graph to answer the following questions. Write down the frequency, the sound emitted by the stationary source. So they're talking about the actual frequency emitted by the sound source. And we just did that whole thing to calculate it. This is 700 hertz. Give a reason for your answer. Because the speed of the car, when the speed of the car is 0, okay, when the velocity of the car, when the speed of the car, because it says speed here, when the speed of the car is 0, okay, the velocity, sorry, when the speed of the car is 0, okay, the speed of the sound source is also 0. So there is no relative motion between the two. Doppler effect is not observed, and therefore the frequency detected by the listener is equal to the actual frequency emitted by the source. So that's why we conclude that it's 700. In which direction is the car moving relative to the source? Is it moving away or is it moving towards? Give a reason for your answer. So again, we're going to use this graph to try and understand that. Okay, sorry, the time is up. So those of you who need to go, you are free to leave. Please, I'm going to finish this question if it takes like 5 or 10 minutes. So if you really need to leave, and then you can watch it later. But if you don't really need to leave, just stay and let's finish this question. Okay, so yes, we understand that the frequency emitted by the source is 700. Then when we see the speed of the car increasing, now we know that Doppler effect is occurring. There is relative motion between the two, and as you can as you can see, there's a change in frequency. But in order to determine whether it's moving towards or away, we need to determine what kind of change is made to the frequency. From 700, it went to 679. So the recorded frequency, the frequency detected by the listener, is less, okay, is less than the actual frequency emitted by the source. And we know that when FL is less than FS, we are in case number 2, which means it's moving away. FL is less than FS. Okay, so it's moving away. Give a reason for your answer, because so you can say as the velocity of the car increases, or the speed of the car increases, so too does the recorded frequency, or the frequency of the listener, which therefore indicates to us that the car is moving away from the stationary listener. Calculate the speed of sound in air. So because it's moving away, you're going to get a mark for showing this formula. FL is equal to V, velocity of speed, the velocity of sound in air. Because it's moving away, I'm going to put minus on top. Velocity of listener divided by velocity of speed of sound in air plus velocity of frequency times frequency source. And now we just substitute, right? The frequency of the listener. By the way, we can either use this or that. It's fine, right? You can use in either case. When the car was traveling at 10, just make sure to use the correct, obviously, frequency detected. Or when the car was moving at 20, just make sure to use the correct frequency detected. So let's use 10. Okay, so when it was 10, the frequency detected by the listener is 679,1. So 679,1 is equal to V is what we want to calculate, minus the velocity of the listener is 10 at that point, divided by V, which is what we want to calculate. The velocity of the stationary source is 0 at all times. Then we have frequency of the source. This was 700. Okay, so let's just simplify it. 679,1 is equal to, I multiply 700 by this, right? Because it's 700 over 1. You multiply numerator by numerator. So 700, open brackets, V minus 10, and divided by V plus 0 is just V. Okay, I can take V over to the other side as multiplication. We get 679,1 times V is equal to, if I distribute this, 700 V minus 7,000. 700 times 10. Now I get my like terms on one side, and I try to solve. So I can take the 700 over, and it becomes 679,1 minus 700. Sorry, they both have V. Is equal to negative 7,000. Let's just... 679.1 minus 700. Negative 20,9 is V is equal to negative 7,000. Negatives cancel. Divide both sides by 20,9. 20,9. Okay, and I get an answer of V equals 334,93 meters per second. If you use the other one, you might get a slightly different answer, but it's fine. It's going to be very close, and that's okay. They will allocate for it. Doesn't the 7,000 have a V? No, because I distributed 700 as a V, and then 7,000 does not. Okay. Okay, so yeah, that's the velocity. Remember, we were expecting plus minus 340 because that's normally the constant. So that's perfectly fine, right? If you're getting like you should get, sometimes you'll even get 350, which is fine, 355. If you're getting like 227, that's something wrong. Okay, so expect around 340 if they're asking you to calculate the velocity of the, what you call it, the velocity of the speed of sound in air, or the speed of sound in air, not the velocity. Okay, so here we don't even have to give like direction. Of course, they just wanted their speed. So that's how you calculate it, right? So they can ask speed. Sometimes they ask what is the frequency of the source. They can ask any of these variables, right? They can ask you to solve for. Okay, so we will have to do another lesson. Maybe we're gonna do another lesson. We have to do a simultaneous example. So this is generally like the hardest question you can get, even so it's not really difficult once you understand it. Okay, and then maybe we'll do another question with some theory. Yeah, we'll probably just aim to do these 3 questions next week, and then we'll move on to the next topic, which is rate of change in chemistry. Yeah, maybe I'll send a poll to ask which one you guys want to do. Rate of change, chemical equilibrium, or acids and bases before you guys do right. Okay, so okay, while you guys are here, you can type in chat or Q&A or host and panelists, whichever one. Which topic do you guys want to do next week or the following week? Rates of change, chemical equilibrium, or acids and bases? Which topic do you guys want to start with? Okay, rate, chemical equilibrium, rate. Okay, so rate, clearly it seems like rate. Okay, so we're probably going to be doing chemical, rate of reactions. When do you guys write? What's the date of your guys' paper? Okay, and what about physics? Okay, but I think for physics, we're done with all the physics terms for physics topics for the term. 14th of June. So hopefully we have about 2 weeks. Okay, cool. So yeah, I'm sure your physics is on term 1 stuff like Newton's and then work energy power. So for physics, we should be fine. And then unfortunately, obviously, there's 2 behemoth of topics, chemical equilibrium and acid and bases. We haven't started yet, but we probably won't be able to do that before the exams. We'll probably just do rates of reactions and then in the holiday, try and catch up, right? We're going to try and push in the holiday. So yeah, let's take that for what that is. Okay, perfect. Okay, cool. Let's end it there. Thank you guys so much for joining. Hope that you guys have a good week. Good luck for any tests that you're writing in the upcoming week. And I will see you guys next week, inshallah, where we will finish up this topic. Oh, sorry. And physics is this topic. So yeah, lucky we finish it by next week. Yeah, then you guys can write your paper. Okay, Jazakallah khair. Ameen. Assalamu alaikum and goodbye.